Namaskar. In this audio video lecture on mechanics, I'll discuss the Hamilton's derivation of Hamilton's equations of motion by Hamilton's principle. We have discussed a lot about Hamilton's principle, and we have also derived Lagrange equations of motion with the help of Hamilton's principle. What is this principle? This principle says that for a monogenic system, for conservative system, for out of all possible paths between 2 points along which a dynamical system may move from one point to another point within a given interval of time, the actual path is obtained by the stationary value of the action integral. Now, what is the action integral? In mechanics, action integral is defined in terms of this integral, in which integrand is Lagrangian and limits are for time from t1 to t2. These are the two time of start and time to reach to the another point t2. So this principle says that the actual path may be obtained with the help of the stationary value of this line integral. That simply means that Hamilton's principle says that for actual path, this delta variation of this integral is 0, because this is the condition for this integral to be stationary. Now, our aim is to derive Hamilton's equations of motion with the help of this principle. You know that this Lagrangian in this principle is a function of qi dot and time, where what are qi? These are generalized coordinates representing a dynamical system. It is a system of n particles and I is going from 1 to n, where in actual this n is equal to 3n. Now, naturally this principle is defined in the configuration space, because your function is L and L is depending on generalized coordinate and their corresponding velocities. And since we have to derive Hamilton's equations of motion, we have to shift to the phase space. Before that, you know that with the help of 1, we have derived Lagrange equations of motion, or you can say if there is some function like f dt, then for by the principle of variation technique, calculus of variation technique, this implies that this is true along the equations obtained with the help of these relations, where this f is a function of qi dot and time. Then this is qi dot delta f delta qi is equal to 0. Now, if it is a function of more than one variable, naturally here also it is a function of more than one variable, so it depends upon the dependency of this function f, that how many relations we will have of the type 2. So, first of all, we will change this L in 1 in terms of Hamiltonian. We know that Hamiltonian is defined as H is equal to sigma pi qi dot minus L, where what is qi dot? It is the velocity corresponding to q, generalized coordinate, and pi is the representing the Pi is representing the momentum of ith particle with respect to the coordinate Qi. So for all I, there will exist such type of momentum, and so H is defined in terms of L like 3. Okay. Now 1 may be written as delta variation of sigma Pi Qi dot minus H, where this H is a function of Qi, Pi and time, because H is defined in the phase space. So comparing, you get a f, you get your integrand. Your integrand is summation Pi Qi dot minus H. And for this integrand, from calculus of variation technique, this 2 should be true. And here you see that you are having 2 coordinates. One is Qi and another is Pi. Right? So what will be the consequences of this equation 2? I have F is equal to sigma Qi dot Pi minus H, right? And equation is ddt of delta F delta Qi dot minus delta F delta Qi 0. This equation is holding for the situation when your generalized coordinate is Qi, or when your function was depending upon Qi. If your function is depending upon Qi as well as on Pi, this will take the form ddt of delta F delta Qi तो रहेगा ही, it will be Pi dot minus delta F delta Pi is equal to 0. 2 implies. And so you will have 2 relations. In fact, these are 2n relations because I is going from 1 to n. And now I'll use the definition of F, which I assigned the name 4, equation number 4. Using 4, this is 4. Delta F delta Qi is minus of delta H delta Qi, because here H is a function of Qi, Pi and time. In fact, I should write it here with H. It is Qi, Pi and time. Now what is delta F delta Qi dot? It is Pi delta F delta Pi is Qi dot minus delta H delta Pi, because H is a function of Pi और यहाँ से भी हमारे पास आएगा Qi dot. And what is delta F delta Pi dot? It is equal to 0. So these are 4 relations which will be used in 5a and 5b. 5b. So 5a implies 5a. You need delta F delta Qi dot. So it is Pi minus delta F delta Qi plus delta H delta Qi. We are using 6 equal to 0. or delta H delta Qi is minus Pi dot. Similarly 5b, ddt of delta F delta Pi dot is 0 minus delta Pi of F. Oh, I have already found its value. It is Qi dot plus delta H delta Pi is 0. Delta H delta Pi is Qi dot. So 7 and 8 are Hamilton's equations of motion. So you see, we can derive Hamilton's equations of motion by Hamilton's principle. And now I'll tell you about an application of these Hamilton's equations of motion for a mechanical system. Suppose I'm talking about, first I write these equations. These are Hamilton's equations are delta H delta Qi is minus Pi dot and delta H delta Pi is Qi dot. These are the equations. Now suppose I have to solve a mechanical system with Hamilton's equations of motion, then what is the procedure? So suppose I take a simple example. I am taking the example of a pendulum. Motion of a pendulum. You very well know that I can solve this motion of a pendulum with the help of Newton mechanics, with the help of Lagrange mechanics, and now with the help of Hamilton's mechanics. So what is the first step? Step 1 is you find Lagrange. L for the motion of a simple pendulum. It is a simple pendulum. L we have obtained with in terms of r and theta, and it was half m. M is the mass of the bob. L square theta dot square minus gl theta 2. This was the bob which reaches to this point. This is L, this is theta, and this is mass. It is to and fro motion, right? So this is Lagrangian. So first thing is that find the Lagrangian. You see here that in this Lagrangian, it is cyclic in R. L is a function of theta and theta dot. So find P theta. Why are we trying to find P theta? That means momentum with respect to this theta, because I have to frame H. H means Hamiltonian. And in Hamiltonian, there is no work of velocity. We will need momentum to be present in H. So whatever coordinate is present in L, we should find its momentum. Theta is present here, so I'll try to find momentum. I know that delta L delta theta dot is P theta, and by 1 delta L delta theta dot is m L square theta dot. So in this way I have found theta dot. Suppose my Lagrangian contains R, some coordinate R, then I'll try to find R dot. If it is containing any other coordinate, I'll try to find its corresponding velocity, because I have to substitute this theta dot in terms of momentum. So this is step 1, find the Lagrangian and then find theta dot. In fact, this is step 2, that find theta dot. And now I'll define Hamiltonian. So it is step 3, define Hamiltonian. H is defined as summation theta dot p theta minus L. If your L contains R as well with theta, then the expression will be summation R dot PR, समेशन नहीं आएगा वहाँ पर, इस तरह से, प्लस थीटा डॉट पी थीटा माइनस एल. But in this case, you are having no R. L is not depending upon R. R is a cyclic coordinate here. So, in expression of H, we will have only one part. So, I have omitted this summation symbol. So, this will be theta dot p theta minus L. You see that in this expression, you have theta dot, you have L, and this L is depending upon theta dot. So this is not the proper form of Hamiltonian. In the proper form of Hamiltonian, you should have only generalized coordinate and generalized momentum. So I'll try to eliminate theta dot so that I may get the standard expression for H. So first I am putting the value of L, and then I'll change or replace theta dots. Right? In this expression, you have theta dots. But for the proper expression of H, H should be a function of theta and p theta only. T is not here, so I am not writing T in H. H is not a function of time. Now, I'll replace this theta dot by this 2. This is p theta upon ml square. Then again p theta minus half m L square. Again this is theta dot square, so it will be p theta square m square L4 minus g L theta square. I'll solve it and find my H. H is equal to theta. H is a function of theta and p theta now, and its value is p theta square upon ml square half of, and then plus half m g L theta square. Now you look at this expression. In this expression you are having only theta, and then this is only theta and then p theta. There is no theta dot here. So you can write that H is a function of theta and p theta. Now you are working in the phase space, right? So in step 3 you have found H. Now we'll use these equations of motion. So for these we need the derivative of H with respect to generalized coordinate, and then derivative of H with respect to corresponding momentum. So I'll find these expressions from 3. Delta H delta theta is equal to mgl theta, and delta H delta p theta is equal to p theta upon ml square. I'll use these two values in Hamilton's equations of motion. So I'm writing Hamilton's equations of motion. Minus delta H delta theta is equal to p theta dot. What is delta H delta theta? So P theta dot is equal to minus mgl theta. You may write it as dp theta dt is minus mgl theta. Now it will be 5. Similarly, from another equation of motion, since delta p theta is equal to theta dot, so I am using this. So theta dot is equal to p theta upon ml square. Now these are, in fact, this may be written as d theta dt is p theta upon ml square. So 5 and 6 are two equations which can be solved easily by using differential calculus or integral calculus, and then you can find the equation of motion. From 5 and 6 you may get dp theta dt d theta dt divided to mgl theta upon p theta ml square. So dp theta dt d theta is equal to minus m square g l cube theta upon p theta. Now it is very easy to solve the two sides. M square g l cube theta d theta. Integrate and get p theta square by 2 minus m square g l cube theta square by 2 and some constant of integration which may be found with the help of conditions, initial conditions. You again know that what is this p theta? P theta was written in terms of theta dot. So you may put this theta dot ml square, theta dot ml square whole square by 2 theta dot ml square whole square by 2 m square g l cube theta square by 2. This constant will be 0, and now solve it and you can get the equation of motion of a simple pendulum. So this is the way to use the Hamilton's equations of motion. In first step you first write down Lagrangian. In second step you find theta dot or r dot or whatever velocity variables are there. In step 3 define Hamiltonian and then write Hamilton's equations of motion, which is in fact step 4. So this is all about the derivation of Hamilton's equations of motion by Hamilton's principle and then its application. Thank you so much.